Hello and welcome back to the course on R programming. And in today's tutorial we will solve the challenge for section 5. So I've already copied the CSV file onto my computer and I've got the vectors file open here in R. So let's go ahead and run all this so that we've got the vectors in our environment prepared over there. And let's make some space over here. So there are the vectors, that's beautiful. Now let's load the CSV file. So comment load data. Now first we'll get the working directory. Okay, that's not exactly what I need to load my data because it's in a different folder. So I'll just copy that and I will set the working directory to desktop/R programming. If I run that, get working directory. Good. Now bear in mind that this is for a Mac. This style is for a Mac. For a Windows, it would be different. It would be something like, let me try type it up here. So it would be C:// actually \/ users \/ curl desktop and so on, right? So you can complete that if you're working in Windows. All right. Now what we're going to do is we're going to actually load the data. We're going to put into a data frame called data, into an object called data, and we'll use the read CSV function. And here we'll say section 5 homework data.csv. Run that. You can see that the data frame has appeared and we can look at it already now. But once again, it's very big. We don't want to scroll through all of this. It'll take time. So let's use the functions that we now know to explore the data set. So head data gives us the top 6 rows. And here we can see we've got country name, country code, region, year, and fertility rate. So what's missing from here? Well, what's missing is, of course, our life expectancy variable, and that is given to us in the vectors. Okay, so that's good to know. Let's look at tail. All right, do you see anything suspicious here? Well, maybe a little bit. You can see that year here was 1960 across the board. Here it's 2013. So that right away jumps out at you if you're paying attention to the data. That's a good thing. That's we noticed something. Plus, we also know that from the challenge that we've got 2 years in the data set. So looks like first it's all of the rows for 1 year, and then it's all of the rows for next year. So let's have a look at the next function, str structure for data. And here we've got 5 columns, and we've got 374 observations, and we've got some factors. Then we've got year, which seems to be an integer instead of a factor. As you can imagine, we're not going to be performing any arithmetic calculations with year, but R is seeing it as a numeric variable instead of a factor. It would have been better if it was a factor for us. But anyway, it doesn't make that much of a difference. So let's look at summary data. What do we see here? Well, here we've got country name, and what you can see right away is, and country code, is that instead of there being 1 record for each country name, there's 2 records, right? And that is in line with what we were told, that there's 2 years in the data set. And then if we look at year, we've got the minimum, the maximum, and a median. So once again, this makes absolutely no sense. And that is because year should be a factor variable. It should be a categorical variable rather than a numeric. So now I'm going to actually show you a quick preview, and this preview is only going to be available for people that watched the solution for this section. So congratulations. And it's going to be an insight into the next section. So we've got a variable here, data. This is what we're going to be talking a little bit about in the next section. So we've got a variable here, data, and it's called year. If I run that, you can see that it's got all these years in there. So what I want to do is I want to turn this variable into a factor, right? We saw that it's not a factor, it's just a numeric variable. Let's say a temp variable, and here we'll say factor. Surprise, surprise, the function name is very obvious, data year. So if I run that, now I've got a temp variable that is a factor. So you can see that it's got all the same numbers, but at the end it tells you how many levels it has. 2 levels. And you can actually check that as separately. You can say levels temp. So there you go. So that's how to turn a normal variable, a numeric variable that you don't want to be numeric, into a factor variable. And in fact, you could even override your existing column with this new temp variable, but we're not going to do that. That was just a quick sneak peek into the next section. All right, so let's get back to our challenge. What are we doing now? What we're doing now is we are going to split the data frame because we have 2 years in one data frame. We want to split it into 2. So let's go ahead and do that. Filter the data frame. All right, how do we filter a data frame? Okay, just because I put this tab and now it's following me around, not good. All right, how do we filter the data frame? We say data 1960. That's going to be our first data frame. Is going to be data, and here we want the filter, right? So I'll create the filter first, and then we'll paste it in there. Year equals to 1960. Maybe remove that space. Okay, so if I run that, you'll see we've got first we've got true, 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 and then we've got false, 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 false. So basically we've created a filter vector, right? Which we talked about in this section. And now if I copy it here, it will tell me which rows I want to take. And don't forget the comma nothing, because I want all of the columns and I want only the rows that will have true in this vector. So if I run this, you'll see that it's a data frame that only has 1960 in it, right? So if you look on the right here in the year column, you'll see that it only has 1960 all the way and 187 rows, so exactly half of the data frame. So if I run this line, I've got the data 1960. Now, same thing for data 2013, let's just copy this line, and here we want equals 2013. Beautiful. Okay, so we split the data frame into two. Now let's do a quick check, because it's always good to do checks for audit purposes. Check row counts, and also we'll get to practice the end row function, which we learned. Data 1960. If you run that, you've got 187. It's a good idea to put a comment here saying that there's 187 rows. And row, data 2013, run that. Once again, 187 rows, and let's type it in, and we can say equal split, which is good, right? Means everything is working as it should be. And also they should add up to 374, which is the total number of rows, and they do. All right, now we want to create the additional data frames, because we have those vectors and they should actually be in data frames so that we can work with them better. Let's do that. Add 1960 is going to be the name of our data frame for the 1960 vectors. Data frame. And so here we're going to use that trick. We're not going to just type in country code, right? We're going to actually say country equals country code, because we want the name of the new column to be country. And then we're going to say life, let's say dot expectancy equals life expectancy at birth 1960. All right. And then add 2013 data frame, and same thing. So let's just copy that. Here we'll say 2013. Right, and by the way, this is life expectancy at birth just on average in that population for that year, and we'll see how they work together with fertility in the final result. So there we go, we've got the two new data frames, which is great. Now let's check them. We'll check summaries this time. We'll say summary, add 1960, right? So there you go, that's your countries, so that should add up to 187. And here you've got your min, median, maximum, and quartiles. And you can kind of understand the life expectancy was never less than 28, which is very low actually, and never more than 73 for any country in 1960. Summary, add 2013. So here you can see that life expectancy increased. So it went from 28 to 48, added 20 years to the average life expectancy across countries of the world. And maximum went up to 83. So the maximum didn't increase as much, but it increased by around 10 years. All right, that's good. Now we're going to merge the pairs of data frames. Let's do that. All right, let's make some space. And how do we merge? Well, we use the merge function. First, we're going to create the object, merged 1960. And here we want merge data 1960, then add 1960, which makes sense, right? The data frame that we split out, this one, and the one that we created over here from the vectors. And then we want, how to merge them? Well, by.x, which column we're going to use in the first data frame? We're going to use country.code. And which one are we going to use in the second data frame? By.y, and here we're going to use just code, because that's the name of the column in this data frame. Okay, so now let's go ahead and actually run this. What you'll see is actually won't run because I named these columns incorrectly. This should be code. I was like wondering what's going on. So this should be code, not country code. So let's rerun those. And now if we try running that, there we go. Now it works. Okay, so be careful with that. Hope you picked up on that while I was typing it. And now we're going to do merged 2013. Let's do same thing, but just for 2013. All right. Run that, and there we go. So both data frames are okay. Let's now check how we're going to check them. Maybe let's check the structure. Hashtag check the new structures, because ultimately we've just created new data frames by merging, so it's a good idea to check the structure and see how they're going. All right, so yep, country code, country name, region, year, fertility rate, life expectancy. So we've basically added that column that we were after, and we just need to make sure that we added the right year to the right year. And same thing, merge 2013. Okay, looks good. So there we go. The only thing I wanted to say here is be careful when merging. So in our case, we know that the number of variables is the same in these, or number of rows is the same in these columns, and there's no duplicates on, so none of these columns is duplicated in their respective data set. If you're merging and, for instance, there's a duplicate in this column code, then what that will do is obviously it will duplicate the matching rows for this data set. So be very careful when merging, and it comes with experience as you merge more data sets, and kind of think of it as a VLOOKUP operation. So if you were doing a VLOOKUP and there was a duplicate in this column or in this column, obviously the VLOOKUP in Excel, would generate not the exact result that you want. So be careful if your data does have duplicate rows or even duplicate values in the columns you're merging on. So you need to take that into account when you're creating merges. All right, so what are we doing now? We're going to get rid of this variable or this column year, because we don't really need it. It's obsolete because we know the year here is 1960 and here is 2013. There's no different years in each data set, and that will be a good chance for us to practice deleting columns. So delete columns. Let's go and do that. Merged 1960 $year, and that's going to be a null. Run that. Okay, and run this one. This is going to be 2013 here. Run that. Beautiful. So now if we run this line and this line, you'll see that we don't have the year column anymore because we don't really need it. We know what year we're dealing with. All right, visualization time. Yay. Library. Don't forget the library, ggplot2. Don't forget you need to install the package. This is actually a package. The function is called library. You need to install the package if you don't have it, but you should by now. Visualize the 1960 dataset. All right, let's do this. Qplot. Qplot to the rescue. How do we use Qplot? Well, let's type it up. Data equals merged 1960. Obviously, you need the data. Then you need X. We were told was supposed to be fertility rate, and Y is supposed to be life.expectancy. Good, that's a start. Then we want color. It's going to be a region, and let's just run that for now. See what we get. Okay, it looks good. It's over here. It's tiny. But it's there. And let's make some space. All right, next we want to do, let's increase the size. Size equals, don't forget about the I, because we want to apply it to everything. And add transparency right away. Alpha equals I 0.6. So if I run that, awesome. The last thing we need is to add a title, main, and I'll say life expectancy vs fertility. Fertility is how many children per woman on average in that country in that year. So if I run that, we've got the title. And now I'm just going to copy that, and I'm going to change this to 2013. It's as easy as that because the data sets are actually identical in terms of the structure. We don't have to change anything else inside. So if I run this, it's going to be the 2013. All right, beautiful. So now I'll show you another trick. Over here, there's two arrows, and actually let's make some space because we don't need the code anymore. We just need this chart, and let's zoom into the chart, and you'll see that here there are two arrows, and you can go back in terms of visualization and forward. And now, just bear in mind that the axis did change, but we can compare the 2 years. So we can see that here, African countries, the red ones, were at high fertility rates, so lots of children per woman, and very low life expectancy, whereas the European countries were at very low fertility, so between 2 and 4 children per woman, and very low, still pretty high, but lower than the African countries, and very high in terms of life expectancy. And what changed in the past, well, not in the past, but in 53 years between the two data sets, what you can see is that the fertility rate dropped substantially. So here it was between 6 and 8 for the African countries. Now, or in 2013, it was between 4 and 6. And the life expectancy increased. So back here it was between just 30 and up to 60, below 60, and now is between 50 and 70. And European countries, these green ones, you can see how the number of children was between 2 and 4, and now it's dropped between 1 and 2 children, so less than 2 children on average among European countries, but the life expectancy has increased. So as you can see, a huge dramatic change. All of these countries are moving from here into the left, top left corner, slowly getting there, and that's where the world is going. And that's exactly the insight, the beautiful insight that the World Bank was after, and congratulations on delivering that successfully. I hope you enjoyed this homework exercise and you were able to practice a lot of things that we talked about. Can't wait to see you in the next section, and until next time, happy coding. Hello and welcome back to the course on R programming, and today we're going to solve the challenge where we need to recreate this beautiful visualization in front of us. So let's dive straight into it. Here I've got R Studio, and the first thing that we will need to do is import the data. So let's go ahead and do that. Import the data. We're going to check our working directory first thing, and here you can see it's not the one that we're after, so let's set the working directory. It's going to be users. There we go. So that is going to set our working directory. Let's run that, and now let's check our working directory again. As you can see, it is the correct one now. Now let's read the data into a new data frame, which we'll call just mov for movie read.csv. And what is our file called? Let me copy the name here. There is the name of our file. So if I run that, and now we've got the data set prepared. Now we'll just quickly do some data exploration as we usually do. So we'll check the top rows. Let's make some space here, and let's rerun this line. So as you can see, there's a lot of columns, and that's why it's taking a few even rows to output all of this. So here we've got the columns. Looks okay, nothing stands out. The only thing is the names, of course, are a bit not the best, but we're actually not going to fix them up because we're not going to be using all of the columns. We're only going to be using some of the columns, and fixing up the names of all of the columns is just going to take time that we don't really need to waste. So let's check the summary. So here you've got your factor columns, as we remember. So all of these words and names, and then we've got some numeric columns as well. And now let's look at the str for move. There we go. So that's all the columns listed over here. All right, so let's quickly decide which columns we're actually going to need in our visualization. Here's the visualization, and we can see right away. X is genre, gross percentage US is the vertical axis. So let's find them here. So we've got gross percentage US, that's going to be our vertical axis. Then we've got genre, that'll be the horizontal axis. And then what other aesthetics, because that's how you think about it, right? So aesthetics are mapped to, they can either be set or they can be mapped. So we're looking for the aesthetics that are obviously mapped to some of the variables in our data, so some of the columns. This is mapped, this is mapped. Then we can see that this is mapped as well, right? Because the budget is one of our columns, and this is mapped. So the size and the color. Size is budget of the movie, color is the studio that produced the movie. So let's have a look here. Studio, we've got a column for studio, and budget. So that's another column that we're going to need. So as you can see, we only need 4 columns. We only need a genre, studio, which have good names, budget million. That's okay. We can remember to copy it from here. 3 dots, then 1 dot, and then gross US. If you feel like changing the names of the columns, please go ahead and do that. You are now comfortable doing that. You have the correct skills to do that. But I'm going to be a bit lazy. I'm not going to change the names of the columns. So now we're going to activate our favorite ggplot2. I'm just going to type this first line here because that's what conventional standards say, or people are just used to doing this, just put it here just in case the person who's running this code doesn't have the package installed from the internet, and then comment it out because we actually do. And then we'll just type in library ggplot2. So if I run that, there we go, we've activated the package. All right, so quickly, what I wanted to show you is a bit off topic, so cool insight. This is not related to a challenge, but I thought this was really interesting about the dataset, and I wanted to show you it right away. So data movie, and then let's have a look at some aesthetics. We'll say actually one aesthetic. I just want to visualize day of the week, right? I want to see when our movies released. So remember previously we'd use geom histogram, but here you can't use histogram because it's not a continuous variable. So here we're using, instead of like a number, a numeric variable, we're using a factor variable. So we've got day of the week here is like Friday, Saturdays, and so on. So instead of histogram for factors or categorical variables, what you need is geom bar. So if you run that, is that you'll see that most of the movies we've got like 600 something movies in the dataset, and over 400 of them were actually released on a Friday. A few on a Saturday, a few on a Sunday, quite a few on Thursday, Tuesday, and then the next like over 100 were on Wednesday. That is, when I saw that, I was quite fascinated because so obviously there are strategies around this. So the studios know that most people go to movies on a Friday, and if you release a movie on a different day, then it's less likely to make a lot of revenue. And the same thing, so Wednesday is like the midweek release. And the other thing you'll find here is that there is no Monday. So it's Friday, Saturday, Sunday, Thursday, Tuesday, Wednesday. It's only 6 days. So never, out of all of these movies that we have in our dataset, not even one was released on a Monday. How cool is that? So they obviously know that if you release a movie on a Monday, it'll be a flop. So yeah, that was just an insight that you can get right away from the data. And this kind of brings me to the other point, which I also wanted to make, that this data set has a lot of information in it. Like, we just looked through it and we said we're going to be only using 4 columns. But in reality, there's so much more information. So I highly encourage you, after you're done with this tutorial on how to solve the challenge, just go ahead and explore and try to set some other challenges for yourself and see what other things you can find in this dataset and what you can visualize. Because obviously we're going to cover some of the skills we learned in this section, but not everything. So we won't be doing any smoothers, we won't be creating scatter plots and so on. So maybe explore the dataset and see what else you can find. Okay, so what are we going to do now? Now we're going to move on to the actual challenge. We're going to proceed with our filters. Why do we need filters? Well, what you'll notice is that in this final visualization, we've only got 5 genres and we've only got 1, 2, 3, 4, 5, 6 studios. In the actual data set, there is much more. So a studio has 36 levels. So there's 36 different studios, and genre has 15 levels. So if we try visualizing the same thing but without filtering our dataset, we'll have a very cluttered visualization. And so there's a reason probably why those filters were applied, and I'll give you a hint. That's because those are the most popular genres and the studios that produce most movies. But what concerns us is that we get the exact same studios and exact same genres, and that will also help us practice filtering datasets a little bit. Right, so let's do this. Filter data frame number 1, or let's say filter number 1 for the data frame. All right, so filt will be our filter, and this is how we're going to create. We're going to say move $genre equals action. So this is one of the genres in the visualization here. So we've got action, adventure, animation, comedy, and drama. So if we do that, that will give us only movies that are in action in that genre. So if I do that and then I say, let's say move to is going to be movie, and then I'll say filt, comma, nothing, right? You remember this? So if I run that, now I will have a data set that only has movies from that specific genre. So if I scroll up here, it's a lot of information. Still a lot of information. So here you can see that all of these movies are action, all of them. That is not what we want. We want many different genres. So we want to say action, and now we want to say or, right? We want to say is either action or it is, let's just put some brackets here. You don't have to put these brackets, but it might just make it more comfortable. So, or here we're going to say adventure, or it is animation, or it is comedy, or it is drama. So we're using the logical or operator, this vertical line, to say one of these conditions has to be true. Either movie $genre equals to action, or it equals to adventure, or and so on. And notice I'm using the double equal sign to check that condition. Okay, so that's the first filter. Now we need a second filter, right? Filter number 2. How do we filter now? Well, now we need to fix up the studios, and we can do the same exact thing. So instead of movie genre, just say movie $studio and then select the correct studios. But I wanted to show you a better way. I wanted to show you kind of like a quick preview of something that we haven't talked about yet. So filter 2, this is just a faster way of doing it. Is if I say move $studio, and then instead of equals, I'll say percentage in percentage. And this operator means that you will give it a vector of values, and then if this matches any of these values, then it will return a true value. So let's say I'm just going to copy the values that we're going to be working with. Basically, I'm just copying these exact words, these exact names of studios. I'm just copying them into this vector. So there we go. So we've got vector. We're creating a vector here, which contains these studios: Buena Vista Studios, Warner Brothers, I probably pronounced that one wrong, Fox, Universal, Sony, Paramount Pictures. So basically this line means if movie studio is in any of these, then it's a true. So choose either way you like. You can accomplish the same thing with this approach or with this approach. This one is just a bit shorter. So let's go ahead and run that. And now I want to combine the two filters, right? So I've got filt, which is filter 1, which is a true, 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 and false. And I've got filt 2, right? So another filter. So how do I combine them? How do I say I want a movie to match this criteria and I want the movie to match this criteria for it to participate in our visualization? Here I have to put and filt 2. So there we go. And now if I run that, this data set will actually only have the movies that we want in the final visualization, and we'll see that as we're creating the visualization. So there we go. We've only now come up to the point where we're going to be practicing our visualization skills, and that's not a problem. That's okay, because we were refreshing our knowledge on filtering data sets, and that's also an important topic, and also worked with some logical operators. Alright, so now we're going to start our visualization process. What do we do first? First, we're going to prepare the plots, data, and aesthetics layers, right? The foundation of our plot. We're going to say P is going to be equal to, or is going to contain, this object is going to contain ggplot data equals mov2, right? That's our filter data set aesthetics. And let's set the aesthetics right away, the ones that we're going to be for sure for the whole plot here, because as you can see, we actually have a few layers. We've got the box plots, and then we've got the jitter in the background. But for both of them, for everything we see over here, X is always equals to genre and Y is always equals to gross percentage US. Now you can't say the same thing about size or color, because the box plots are not colored by studio, and their size is not affected by budget. So that's why we're not going to include those aesthetics in the base or in the foundation of our plot. We're only going to include the two aesthetics that are definitely going to stay constant. So genre and gross percentage US studio. So how are we going to do this? We're going to say X equals genre, and then what do we want? We want, let's just go to the top here. We've got the name of the column here, right? So genre and Y equals gross percentage US. So if I run that, if I try plotting it, I'll get nothing, because obviously we don't have a geometry. So now let's add a geometry, right? So we'll start by adding the simplest geometry that we know is P plus geom underscore point. All right, so if I run this, you'll see that I get these just points aligned with the categorical variables over here at the bottom. And already you can see that we've got action, adventure, animation, comedy, and drama. So the correct 5 genres that we were after, so our filter worked. All right, so obviously jump point is not what we need. Let's try box plot. Jump box plot, you can see that there is our box plot. That's a good start. That's already looking similar to what we have here, yeah? But at the same time, you can see these black dots. So let's just pay attention to that. Let's quickly make a note of that in our heads, that these dots are actually part of the box plot geometry. As you can see, we don't have any point or other type of layer, and so basically these outliers are part of the box plot geometry, and we'll need that information just now when we're fixing up our chart in a couple of steps from here. All right, so we've got the box plot. Let's add the jitter, right? So in the background we saw jitter, so let's add that. So if I run that, you can see we've got the jitter, but in this case it's on top, right? We want to put the jitter in the background, so let's do that. There we go, the boxes are on top, but now they're covering the jitter, so let's give the box plot some transparency. Do you remember how to give transparency? It's the alpha parameter. We're going to set it to 0.7. Now notice that we're not creating an aesthetic here. We're not, well, alpha is an aesthetic, but we're not mapping it to anything. So we're not using the AES function, because we're actually just setting it to a certain value, 0.7, for all of the box plots. And because we're specifying this alpha inside the brackets for jump box plot, it's only going to be applicable to this layer. It's not going to be applicable to the jitter layer. All right, so if we run that, we can see that the box plots are a bit transparent now, which is good. All right, so now we want to add size and color to the points. Remember something that we didn't do here, because the size and color are only applicable to the jitter layer, and that's what we want to do. So we're going to add it here. We're going to use the aesthetic function because what are we doing? We're mapping. We're not setting, we're mapping. So size equals, what does size equal to? Budget, and color equals studio. Now, studio, we remember that that is the correct name, but let's check what the name for budget is in our data set. This is kind of the consequence of not changing the names of your columns. Okay, well, there's not enough space, so we would use something like str. Let's just run that quickly and find it here. So there we go, budget mil. That's the one we need. So size equals budget mil. So I can start with that. You'll see the size increase. Good. And now I can add here as well, color equals studio. So if I run this, you'll see that the color has appeared. And also the studio filter worked because we only have the 6 studios that we are after. So there we go. That's a good start. Where else do we need? The other thing I wanted to show you here is that you can still see these black dots, right? You can see there's that black dot, there's those 2, there's those 3, and there's that 1. And in fact, these are part of the box plots, not these are not part of the jitter. As you remember, we saw in that first time when we just added the box plot layer, they were already there. And you can see that this green point is in fact the same dot, but it's just jittered to the right. And here, for every dot in the box plot, for every outlier, there's a dot that is already added by the jitter. So in fact, what we need to do is we need to get rid of these outliers. We don't want to see them because they're already present through the jitter layer. How do we do that? Well, in the geom box plot, there's a parameter called outlier.color, and we just need to set it to NA. So meaning we don't want a color at all. And as you can see, those dots have disappeared now, and there's no duplication of information on our chart. Okay, good. So what we're going to do now is we're going to save this into, well, save in quotation marks, because we're just going to kind of create a new object which will contain this whole visualization, right? So if I just call Q here, then you'll see that visualization is ready. And now we can proceed with the final finishing touches because we're nearly done here. It's that quick. So we're just going to do the non-data inc part. We're going to say Q. We'll just override Q with Q plus, so just give it some little adjustments. We'll say xlab is the bottom axis. We'll say xlab is going to be called genre. Then we'll say ylab is going to be called gross percentage US, just like in the chart that we saw, and gg title which is the title of the whole plot, is going to be called domestic gross, what was it there? Percentage by genre, right? Okay, so if I run all of this and then I plot Q, you'll see that all of these titles have now appeared, and that's a good start. Now what we have to do is fix up the theme layer or add a theme layer. We're going to say Q is Q plus, and now we just want to make these bigger, add the colors, change the font, and so on. So how do we do this? Theme, and inside theme we're going to start by changing the colors, right? So we'll say axis dot title dot x is element text color. This is the axis title, which is genre, and it's blue here, so we'll say blue. And the size, well, this is kind of a method of experimentation. In this case the correct size is 30, but you could set like 20 or 25 and it would be, I think, close enough. All right, so that's the x-axis. Let's do the same thing for the y-axis. The color is blue, size is 30, exactly the same. Okay, so now we want axis, not title, but instead we want the text. So that's these little marks here, 80, 60, 40, 20. As you can see, they're a bit bigger there than we have. And the color was still black, so we don't need color. We just need the size, and we'll set it to 20. And same thing for y. Okay, so let's quickly run that and see how we go. Obviously get rid of this comma for now. If I run that, you'll see that already it's getting better. The only thing is we haven't changed the size of our plot title, so let's do that quickly. Plot.title equals element text color. It's actually black, so we don't need to change the color. We'll just say size equals 40, and then also the legends, right? The legend title and the text. So, or I mean the text of the different names or categories in the legend. So you can see here, this is bigger, and the size of the text is actually, we'll just actually change it as well. So legend.title is going to be, let's copy this and say 20, and here finally we'll say legend.text. So if I run this, what do we get? Okay, it looks much better. So what do we still notice? We notice that the font is different. So here it's the standard font, here it's Comic Sans MS. How can we fix that? Well, one way to fix it is to, in every single one of these, to say comma family equals Comic Sans MS, right? That's one way of doing it, and let's just run that one. You'll see that the plot title has changed, and now we have to do the same for every single one of them. But that would take quite some time, so I'm going to show you a shortcut. Instead of typing it up every single time, what we can do is we can say text equals, and then the same thing, element text, and then here we'll say family equals Comic Sans MS. And this will apply to all of the titles and texts on our plot. So if I run this, you'll see that they have all changed to Comic Sans MS. Okay, voila, nearly finished. Just one final touch over here. Budget mil needs to be changed to budget dollar millions or M. And how do we do that? Well, this is another thing that we haven't discussed yet, but it's actually very simple. So final touch. So Q dollar labels dollar size, and we need to assign it. What do we need to assign it? We want to say quotation marks budget dollar M. So if I run that and I look at Q now, as you can see, the name of this label has changed. The name of this legend has changed. All right, so there we go. That's how we solve this challenge. I hope you enjoyed this walkthrough, and I look forward to seeing you next time. Until then, happy coding. Welcome back to the advanced course on Tableau. In the previous tutorial, we created these beautiful 4-box plots, and today we're going to learn how to analyze them. We've got quite a lot of ground to cover, so let's jump straight into it. First off, I would like to make sure that everybody is on the same page, and therefore let's look at how exactly box plots work. So I'm going to bring up a slide that I've prepared. Very excited about this. All right, so let's say you have an axis. It can be vertical, horizontal. In our case, it's vertical, so let's stick with that. And you have a certain number of observations that you can plot on this axis. So there are our 10 observations. Now, in order to create a box plot, what you have to do is you have to physically count the number of observations, so 1, 2, 3, up to 10, and then take the middle between them. So in our case, there's an even number of observations, so there is no one middle observation. The middle ones are 5 and 6, so we're going to put a line exactly between the fifth and the sixth observation. Now, what we're going to do is we're going to do the same thing for the top 5. Here we've counted, we have 5 observations. The middle one is number 3. We put a line through that one. Now let's do the exact same thing for the bottom half. 1, 2, 3, 4, 5. This is the middle one over here. So we put a line through it. Now, if we replace these lines with a box, we are slowly starting to create our box plot. Now, all we have to do is plot the whiskers. So the whisker goes all the way up to the top one over here, and the other whisker goes all the way up to the bottom one here. And elements of the box plot have their own names. This is the minimum, this is the first quartile or the lower quartile, this is the median, this is the upper quartile or the third quartile, and this is the maximum. And just make sure you don't get confused here. This is not the mean, this is the median. And that's because of the way we've constructed it. So that is how a box plot gets built. So basically it's about counting the number of records and breaking it up into 4 quartiles. So every single quartile has an equal number of records in it. Now let's look at another example. Here we've got another axis, we've got our observations, and let's do the same thing. So that's our median. That is going to be our first quartile. That is our third quartile. Now if we connect them, that's our box. And now what we can do here is if we measure the distance between the third quartile and the first quartile, it's called the interquartile range. Well, the way we construct box plots is we want to make sure that our analysis is not affected by outliers. So if any observation falls too far away, then we want to exclude it from the construction of the box plot. And how do we determine if an observation is too far away? Well, you need to take 1.5 times the interquartile range, and that is going to be your cutoff point. So if an observation falls further than that, then you shouldn't include it in the box plot, and it's considered an outlier. So in this case, our box plot is going to look like this. And that separate dot out there is considered to be an outlier. Alright, so that's how box plots are constructed. Now let's have a look at a few sample use cases of box plots. So here I've got a horizontal axis, and for a change we're going to be looking at horizontal box plots. And to make things interesting, let's say we're analyzing sales representatives and their daily sales. So what would you rather? Would you rather have your observations plotted like this, or would you rather have your observations plotted like this? In both cases, the median is the same. It is $1,000. Now, this is where we can look at a box plot, and if we create the box plot for the first example, you will see that it is quite compact like that. The second box plot is much more wider. So what does that tell us? That tells us that the variance in the first box plot is lower. So you have more chances of being closer to the median. You can only, from the observations that we have, you are only going to be somewhere between these two whiskers, and more likely you're actually going to be inside the second and third quartiles groups, and therefore you're more likely to be next to the median. Here you have more room to go up, but you also have more room to go down. So that basically means that the risk is higher, or the volatility is higher, and your sales reps can bring, they do bring a median back over $1,000, let's say, per day, but at the same time it can really vary. It can be anywhere on the right, anywhere on the left. So you have more certainty with a more compact box plot. You have less certainty with a wider box plot, even given the same median. And the way to think about it, or another way to think about it, is in terms of distribution. So this distribution is narrower, this distribution is wider. So if we talk in terms of standard deviations, the standard deviation is here, which is also a measure of variance, right? So here the standard deviation is higher or larger. Here it's smaller, so you have a narrower distribution, and you're more likely to actually hit the nail on the head here whereas here you can either go left or right, which is more uncertain. Okay, let's have a look at another example. Can you tell me right away, what do you think? Is this a good box plot or a bad box plot? Let's say we're also measuring sales, and now it's a vertical axis. And of course, it would be better if it were compact and were like this, but is this a good box plot or a bad box plot? And given that the minimum and the maximum are fixed. And in essence, the question that we're asking is this box plot better than this box plot? And if you think of it in terms of median, the median here is higher than the median here, and it makes the answer obvious. Of course, this box plot is preferable to this box plot. So basically, if your minimum and maximum are fixed, you want your box, the box part of the box plot, you want it to be as higher or as closer, as more closer to your desired result as possible. So here we're talking about sales, so the larger sales or higher sales are better, so we want the box to be higher, not lower. But that is the obvious answer. How do we think of it in terms of distributions, and how do we think of it exactly why this is the case? So if we plot them now sideways, so this is the good box plot, this is the bad box plot. Let's plot the observations that make these box plots happen. So these are our 10 observations in this case, and these are our 10 observations in this case. How do we see them in terms of distributions? And for me personally, this is the part that drives this point home. This is what makes things click. So I'm going to plot the distributions here. And this here, you can see that this is a right skewed distribution. And by the way, right skewed is because the tail's on the right, we don't look at the hump, we look at the tail, where the tail is, and that is how we define whether it's a right skewed or a left skewed distribution. So this is a right skewed distribution, and if you think of it in this sense, what it's telling us is that if you throw a random observation, another one observation onto this chart, then it is more likely to end up in this area, in this more dense area, than it is in this tail part, right? Because that's how distributions work. There are more observations here, so you got your mean, median, mode in this part of the chart, not in this part of the chart. So you throw a random variable here, it is more likely to end up here. And here on this other side, if you throw a random variable into this environment, into this example, then what will happen is it will more likely end up on the right side. So this is a left skewed distribution, the tail's on the left, but most of the observations are concentrated over here. So if you throw another random variable, it will most likely end up here, and which is good for us because the sales are higher. So that is how I personally think of box plots sometimes, because you know, like distributions, we're used to them, and they've got a lot of mathematics behind them. They've got standard deviations, things like that. Box plots are also great, but they're simpler things, I think. And when you think of them in terms of distributions, it makes a lot of sense that why a box plot which looks like this is worse if you want to be on the right of the axis than a box plot that looks like that. Okay, so that is how box plots work. Let's now jump back into Tableau and see what analysis we can derive from them there. All right, so there's our chart. What can we see from this chart, knowing that everything we know now? Well, right away we can see outliers here and here. So what this means is that in these three states, in New South Wales, Queensland, and Victoria, there are companies that are underperforming in terms of the overall performance in that specific state. Then in Queensland, there are companies that are overperforming. Also, if you put your mouse over the box plot, you will get some information which directly relates to the 5 points that we discussed about box plots. So the minimum, the lower quartile, the medium, the upper quartile, and the maximum. And if you use this information, you can compare the box plots among each other. And for instance, we can say that this box plot has the highest median, which is 8%. This one is also 8%, but you can visually see that it's lower. Then this box plot comes in a third. So this state has the third median, which is 6%, and this one has 4%. And finally, let's talk about the variance and the sizes of the box plots. You can see that this box plot here and this box plot here, they are pretty big compared to these two box plots, and that means that the variance here is much greater. So there is less certainty that like a random company thrown into this one of these states will be performing at the median net profit margin. And bear in mind, when we say random company, we're not taking into account all the amazing things about our specific company. We're not taking into account the product differentiation that we can offer, the amazing customer service that we deliver, and all those great things. We're just saying if we throw in a random company that performs comparably to the companies in that specific state, and it's performing about somewhere around average with a certain level of variance, where will it end up? So it is likely to end up in this box, but because the box is so big, there is more uncertainty as to where it will be performing in this specific state. So basically, we're kind of assessing the business environment in each of these states. If in Western Australia, once again, there is more uncertainty where your company will end up in terms of net profit margin because the box plot is quite large. Here, the box plots are smaller, and as you remember what we just discussed, which one is better? Let's say here, would you rather have this box here, or would you have it up at the top? You would rather have it up at the top because the higher net profit margin is better for us. So this is not the best setup in this specific state. It could have been better. If this box had been higher at the top, would have been better. On the other hand, in Victoria, you can see that the box part of the box plot is at the top, meaning that the setup in this business environment is actually pretty good. You can see that the box plot is quite compact, meaning that there is less uncertainty in terms of where a random company would end up in terms of net profit margin. And also you can see that the median, well, of course, the median is higher than these two other states, but also you can see that the box part of the box plot is closer to where we want to be, to the top. And as we discussed, that's a good thing. That's better than if this box part was lower. So there we go. That's how you analyze box plots. And what can we conclude from here? Well, we can say that out of these three states, since we are already working in, or the business is operating in New South Wales, out of these three states, it's obvious that this state, Victoria, is the better one in terms of expansion, in terms of business environment. And this analysis has been performed based on competitor research. Now, that's not the end of our challenge. We, of course, have to analyze the economies of these states. We have to analyze how the industries are performing and how the populations are growing, things like that. So we will definitely get to that. This was like the very first stage. And what we want to do now is we want to use the rest of our analysis and hopefully back this finding that the business environment seems to be best for this specific industry at this specific time in Victoria. And I look forward to seeing you in the next tutorial. Until then, happy analyzing.